Our objective is to estimate the fractional amount of the original oil in place that is ultimately recovered as we inject fluids into injection wells and recover oil from production wells. This fractional amount is the recovery efficiency and has three components: the aerial sweep efficiency, E sub AS, that is, the fractional area of the reservoir that is contacted by the displacing fluid; the vertical sweep efficiency, E sub VS, the fraction of the reservoir's vertical cross-section that is contacted by the displacing fluid; and the displacement efficiency, E sub D, the fractional amount of oil contacted that is actually displaced to a production well. The product of aerial and vertical sweep efficiency tells us the fractional volume of the reservoir that is contacted by the displacing fluid during an improved recovery operation. We shall refer to this product as the volumetric sweep efficiency, E sub V. The displacement efficiency is the fraction of oil in this swept volume that is recovered. The volumetric sweep efficiency depends on three key factors: the relative mobility of the displacing fluid to that of the oil, the injection and production well pattern, and the permeability distribution of the reservoir. Let's consider the first factor. The mobility of any fluid in a reservoir rock is its relative permeability, K sub R, divided by its viscosity, mu. If one fluid is used to displace another, the ratio of the mobility of the displacing fluid to that of the displaced fluid is referred to as the mobility ratio, M. When M is greater than 1, the displacing fluid, perhaps water or gas, moves faster than oil and will very likely bypass some of it, resulting in a low sweep efficiency. On the other hand, if M is less than 1, the oil is capable of moving faster than the displacing fluid, and we have good sweep efficiency. Since we cannot easily alter the reservoir's permeability, we have only two choices for reducing M and thus improving recovery. We may reduce the viscosity of the oil or increase the viscosity of the displacing fluid. We can reduce the oil viscosity by heating it or increase the viscosity of the displacing water by adding some polymers to it. Polymers thicken it, as we see here. Now let's turn to the second important variable influencing the aerial component of the volumetric sweep efficiency, the well pattern. Studies have shown that when we have a homogeneous reservoir and a 5-spot well pattern, the aerial sweep efficiency at breakthrough for M equal to 1 is about 70%. On the other hand, if we have a 7-spot well pattern with 2 injection wells for each production well, the aerial sweep efficiency increases to 80%. The particular well pattern for a reservoir generally depends on the reservoir properties and project economics. The third variable controlling sweep efficiency is the permeability distribution, especially aerial and vertical variations in permeability. Natural fractures or permeability streaks will cause the displacing fluid to finger through the reservoir, bypassing quantities of oil, yielding a low sweep efficiency.
We now understand the three variables that control sweep efficiency. But what about displacement efficiency? Isn't it enough just to get the displacing fluid to contact the oil? The simple answer is no. Oil is not displaced in a piston-like manner.
As fluids move within a porous medium, the displacement efficiency is determined by the size and nature of the pores, the rock wettability, and the interfacial forces that exist between the fluid phases. Here, for example, we see a representation of what occurs as water displaces oil in a reservoir. Some of the oil is displaced early in the drive. A little later, even more has been pushed ahead, but we also begin to see that because of capillary forces, oil volumes become isolated within the pores. By the time the displacement is complete, 20 to 30% of the remaining fluid volume may be residual oil. The displacement efficiency then may be 70 to 80% rather than 100%. It can be improved, though, if we reduce or eliminate the forces at the fluid interfaces.